So please read the problem. What it says is that you're required to determine the resultant internal torque at points A, B, and C, which are located just to the left of applied torques. So I think it's the best that I solve it on the board for you quickly. What we do in this case, as in previous cases, we start by drawing free body diagrams. Let's say we want to find the torque at point A. So this is again finding forces or moments. And to do that, I'm going to take a section at exactly at point A, which lies to the left of this torque, right there. I'm going to take a section and draw the diagram. So it's going to look something like this. And there is a 10 Newton meter torque on the back end in that direction. And to balance that or to keep it in equilibrium, I will have to have a torque which I'm calling TA. And just as a reminder to you, the sign convention we follow for these torques is as follows, that you take the positive x-axis coming out of the perpendicular to the surface cross-sectional area, and then you point your thumb in the direction of positive x, and then curl your fingers in the direction of TA, then this is a positive torque. Now, if you apply this to the other torque, you will find that if you curl your fingers in the direction of 10 Newton meter torque, your thumb is pointing in the negative x direction. So this is a negative torque. In other words, when I write the equation of equilibrium for these two torques, it will be like this. TA is the positive one, minus 10 equal to 0. Therefore, TA is equal to 10 Newton meters. That's the answer for TA. Everybody good? Any questions, anybody? All right, let's move on to the second part. That means we want to find the torque at B. So again, I'm going to draw a free body diagram, which will be taking a section at B. Let me do that. And this time, let this be B, and then I have the 10 Newton meter there. I also have a 20 Newton meter at A or close to A, which is this. And then I'll have to have a torque coming out at B, and that I'm going to call TB. So let's say I just take any direction. I don't know what direction it's going to be, but let's say I assume this has the direction for B. And once again, that's my positive x-axis. So which one of the torques is positive? Well, 10 Newton meters is negative, 20 is positive, TB is also negative the way I've shown it. So let's write the equation of equilibrium. It will be minus TB plus 20 minus 10 equal to 0. Therefore, TB, if I transpose it to the other side, will be equal to 10 Newton meters. Positive means it will be in the same direction. So I find 10 in that direction. And it stands to reason because this 20 will have to be balanced by this 10 plus this 10. So likewise, you can find TC. I don't think there's any need for me to go over that. I'd like you to finish this problem, find TC also, and you will notice that TC will come out to be 40 Newton meters, so that the whole thing balances out, is in equilibrium. Any questions, anybody?
Nope.
Did you have a question? No. All right. So let's now then move on to what we have to talk today. And today we are going to start with our next chapter, which is on the chapter 1, the real part of chapter. That means we start talking about stress. Up until now, we were talking about statics. Now we start with strength of materials, so mechanics of materials, and that is the first chapter is entitled stress. So you all have heard about stress. Now let's define this stress and see what causes stress. So basically the thing is that if you see you have a member, for example, do you see this member I have shown, and I've borrowed a picture from your textbook. If you have a member like this, and the member is axially loaded, so you have a force P in one direction, and to balance that, to keep it in equilibrium, there have to be a force P on the other direction also. So you're kind of pulling at this member on both ends, applying a tensile force to the member. What will be the effect of this on the member itself? Well, the best way to analyze is to define a property which depends upon the area of cross section. You see, that's the area of cross section on which this force P is applied. So obviously, if you increase, let's say you double or triple this area, then the effect of this force will be reduced on the member. You see what I'm saying? And if you reduce the area a little, then the effect of this force will be felt more by the member. Do you see what I'm saying? So that is why we define stress based on the area. And here is the formula given to you on this very slide. So the stress and the way this is called a normal stress, for the reason that your force is perpendicular to the area on which it is acting. So normal as in perpendicular. This is called a normal stress, and normal stress is designated or represented by the Greek letter sigma. And sigma is equal to P over A. So P is the load applied, A is the perpendicular area, or perpendicular area of cross section, you can say. So sigma is equal to P over A. This is a basic formula. This you have to know, you have to remember. I don't expect anybody to go back to the equation sheet to check this formula. I mean, this is going to be your bread and butter throughout this term. Sigma is equal to normal stress defined as P over A. Now, if you see this P over A, and maybe I can actually go on to the, by the way, before we go on to the next slide, what are the units of this normal stress? You are defining normal stress by sigma is P over A. If we talk about SI units, then P is measured in newtons. That's the load applied or force applied. That's measured in newtons, and area is measured in meters square. So really, the units of sigma are Newton per meter square. And to honor the scientist who initially worked on this, whose name was Pascal, a French scientist, physicist, this unit is called a Pascal, and in short written as uppercase P with a lowercase a, PA, Pascal. But as you can see, Newton is by itself a very small unit of force, and meter is a large unit of area. Meter is pretty big. So Newton per meter square becomes a very small unit of stress. Pascal is a small unit. So usually you will find that you will never be talking about Pascal. It will be either, for example, kilopascals, which means 100 pascals, or megapascals, which is MPa, means pascals times 10 to the power 6. This is pascals times 10 to the 3. This is pascals times 10 to the 6. And likewise, gigapascal, which is 10 to the 9th pascal. So you might find these units many times in problems that the stress on a certain member is so many gigapascals, because just because pascal is a very small unit, so you normally at least megapascal, you will find usually the stress is measured in megapascals. Also could be kilo or gigapascals. Now coming back to the formation of stress, or the formula for stress, sigma is defined as P over A, and A is the area. So if you had, that's your member, there's your P, this is your area, and sigma is defined as P over A. Now this P over A is a stress which can be shown. This will be acting on all parts of the area. Any little portion of this area you take, it will have the same stress, sigma. So this is what I'm showing you in the next slide there, that P over A is taken as, you can see that this is being shown as a constant stress all over the area. And the area here, what I've drawn on the board is a circular one, but this one is any general area. That's why it looks like this. There's nothing much to it. You could have an area in any shape or form. It will still be P over A, the sigma. And notice that when you take out a small little cube from there, what you are showing is sigma as the stress on this surface. But to balance this sigma, there has to be another sigma in the opposite phase to keep the equilibrium, just because you had the P there also. So there will be a P here also, and this causes, so it is always shown in pairs. That's what I'm trying to say. That whenever you have a sigma on one face of your member, there will be an equal and opposite stress on the opposite face to keep it balanced. So you always show them as pairs for members which are in equilibrium. Now, this kind of a stress which is caused by a tensile force is called a tensile normal stress, and the opposite one, which is caused by a compressive stress, is called a compressive normal stress. So this is tensile, this is compressive. This member is said to be under tension, and this member is said to be under compression. Compression is shown as in the opposite direction, tension is shown in this direction. In general, if you remember, tension is taken as a positive force and compression is taken as a negative force. So not so much, I don't think it's so much used in stresses, the positive, negative sign. You can talk about tensile and compressive stresses, but generally you don't talk about positive and negative stresses, no. Just the proper noun is used. Either the stress would be tensile or it would be compressive. And we don't use positive and negative stresses as such. So both of them have the same units, obviously, whether it is positive, whether it is tensile or it is compressive, the units will still be the same pascals. Any questions, anybody? So this is what we call the normal stress, sigma. Now we go on to look at the next step, the next kind of stress, which is called shearing stress. So basically stress is of two types, normal stress and shear stress. Now the normal stress we just talked about, it's called sigma. Sigma is defined as P over A. It can be tensile, it can be compressive. But when we go on to look at shear stress, how are shear stresses formed? This you will be able to see in this particular slide, which is showing you the formation of shear stress. And if you see, let's say you had a member, something like this, which is supported by two members at the bottom, you apply a load here, then the main thing about shear stress is that shear stresses are formed on surfaces which are parallel to the applied force. Remember in the case of normal stress, we said that the stress was formed on area perpendicular to the force applied. So if this is the force applied, the perpendicular area is this upper one. That would be the normal stress. That will be the normal stress due to this force. But the shear stress is on areas which are parallel to this. Which are those areas? These are these areas you can see there, which is this area, this cross-sectional area there, or this cross-sectional area there. So that's the first thing you should note, that shear stresses are caused on or are defined for areas which are parallel to the applied load. If applied load is this F, then the shear stress will appear on these two surfaces. Just like normal stress will appear on the top surface and the bottom surface, the shear stresses will appear on these sides, on the areas which are parallel, which is shown here. So the way to show shear stress is by small little arrows all over the area, like this. Just like we were showing the normal stress by perpendicular arrows all over the area, remember that? I can go back a slide and remind you again. So this one, we are showing the normal stresses in perpendicular, arrows perpendicular to the surface area. And for shear stresses, we show them lying, small little arrows going all over. And shear stress is represented by the Greek letter tau, defined as V over A. V is the shearing force, and shearing force is this force V. So V divided by A. A is the area parallel to the shearing force. So if this is the shearing force, then this is the area A. V is the shear force and A is the parallel cross-section area. And once again, the units of tau remain to be the same because it's the same kind of thing. It's force divided by area, Newton per meter squared, which is Pascal. So for both normal stresses and shear stresses, the units are the same, Pascals. And the definition is sigma and tau. Sigma is P over A, tau is V over A. Yeah, it will be. You're right. Because you can see that V will be equal to 1/2 of the force, right? Because there are two V's. So the shear stress will then be V divided by area, which will be F over 2 divided by the area. So it'll affect, yeah. The fact that two surfaces are now taking it will affect it. All right. Now, any other questions, anybody? Well, there's something I want to show you about shear stresses, which you need to understand because it is going to stay with you and you will have to be using it again and again. So the first thing is that shear stresses are defined for parallel areas as opposed to normal stresses, and I would say tau is equal to V over A is the basic formula for shear stresses. Now, for example, if you had a cube like that, how many surfaces does a cube have? 6. You can see three of them right there, and the other three, maybe I can just try to make it a three-dimensional thing. Now you can imagine the other three surfaces also. So one top surface, one bottom surface, one right side surface, one left side surface, one front surface, one back surface. So that way it has, a cube has 6 surfaces. Now what happens is that suppose you had a shear stress there, tau. This means because there is a shear stress in this direction on this surface, which is parallel to this, it means there is a force in this direction. And if there is a force in this direction which is causing this stress, then this block will have a tendency to move in the direction of force. So therefore, to balance that, if you have a shear stress on one face, there has to be a shear stress on this face in this direction so that it balances that shear. You see what I'm saying? So whenever there, so the bottom line is that shear stresses do not occur just on one surface. They have to be on more than one surface. For example, as I explained to you, if this is the shear stress on this face, then there has to be an equal and opposite shear stress on this face to keep it in equilibrium. And if that be so, there will be two more stresses to complete the equilibrium, which will be one on this face. So let me define those faces also. If this is your XYZ axis, let's say, if this is the x-axis, this is the y-axis, and this is the z-axis, then this face, which is perpendicular to the x-axis, is called the x face. And the face opposite to this on the other side of the cube is called the minus x face. Similarly, this face, which is perpendicular to the y-axis, is called the y face, and the one on the opposite side is called the minus y face. And then this face, the top face here, is called the z face, and the bottom here is called the minus z face. So all the 6 are defined. So if I have a tau on the z face, it will require that there be a tau equal and opposite tau on the y face, and similarly for this tau, there will be another one on the bottom face in the opposite direction, and one on this side like this and like this. So that is really now this is a three-dimensional picture, so you're looking at it like this. But if you were to look at it from the x face side and draw a two-dimensional picture, it will appear something like this. This is the first one that I drew, the tau on top face, and to balance that, there was a tau there. And then to balance these two, there will be two more taus. So this really completes the two-dimensional picture of that cube, which is in equilibrium. For this cube to be in equilibrium, if you had just one tau, it will result in having 3 more taus like this.
Dr. Rossi?
Yeah.
So if we have a force going along with the tau, wouldn't those force, or wouldn't the stresses be on the side be perpendicular, making it normal stress?
So you mean for this, if there is a force in this direction?
Yes.
Then you consider that force on this face, it will become a normal stress for that face. But this force is acting on this face.
Okay.
And there it is parallel. You see what I'm saying?
Yes.
All right, good. So now this is the thing I want you to please understand and practice it. That if ever you are given a tau with, so if I give you that this is a two-dimensional little cube that I'm showing, it becomes a square in terms of 2 dimension. And let's say I gave you that this has a tau on this face like this. Now, to make it in equilibrium, you should be able to complete all the other three taus and their correct directions. For example, if this is the tau I have given you, then what will be the direction of tau on the top surface? To balance that, it will have to be like this. And then the other two surfaces would be something like this. But it turned out to be exactly the same. Now, again, suppose, let's say I gave you a tau something, a two-dimensional square like this, and I said this was a given tau there. How will you complete it? I'd like you to do it in your notebooks, for example. Just complete these stresses for this little square, the way we have discussed it. And to compare your answers, you can see this will be like this will be like this, and this will be like this. That's the correct way. You will always have to be showing at least 4 taus in a two-dimensional thing. And this brings me to the next topic, which is called the general state of stress. By the way, it's exactly the same for the normal force or normal stress also. For example, you had let me show you a little cube there. And if I had a normal stress there, where will I need to have a balancing normal stress? On the bottom surface, like that. So there will have to be an equal and opposite normal stress. So on the cube, just 2 will be enough for equilibrium. But for tau, for equilibrium, there are a minimum of 4. All right. There could be more normal stresses. I could have another normal stress on this face, for example. Then to balance this, there would be one on the back face also. So it will be somewhere there. I don't know how to draw it in 3 dimensions, but there will be a normal stress. To balance this one, there will be another one on the back face. And if there was one on the y-axis side, then there will be one to balance that one. So there are also 6 normal stresses, one on each face of the cube. And every 2 will be equal. They have to be equal and opposite. These 2 have to be equal and opposite. These 2 will have to be equal and opposite. These 2 will have to be equal and opposite. You see what I'm saying? Yeah. Mm-hmm. No. Well, there could be, the stress, it's not necessary that always the force will be in the direction. So there could be if you're considering this front face, there could be a tau in any other direction. But then what we do is we then consider the square that we take is like that. You see what I'm saying? And when we draw it separately, it still can be shown in the same way. It could be at an angle also. In other words, that's what I'm saying. It's not necessary that always tau is in this direction in a member. Stress can also be in a different direction. But then we tend to take it so that it becomes parallel to the top surface. Did that answer your question? All right, good. Now maybe I can try and draw this, or you can see it in the book also. I'll show you in the book also. But the general state of stress. Let's talk about the general state of stress, which is actually I can use the same cube. I'm showing you the 4 taus there. There could be 2 more, shear stresses, and they would be one on the front surface or the X surface, which is not shown here, and one on the negative X surface. And also there could be normal stresses. There could be a sigma on this face. There could be a sigma on the bottom face to balance that. Then there could be a sigma on this side. and a sigma balancing that on this side, and similarly a sigma coming out here and a sigma going out on the back end. So all the 6 faces have sigmas, and all the 6 faces could also have a shear stress. So if you have a shear stress like this on this face, there will be one to balance that on this face and then 2 on the other end also. So it becomes a little messy, but the book has shown a nice picture. I'll highly recommend that you go and look at that one. So maybe I can pull it out and show it to you also. The general state of stress. Where is it? Lost it completely. Oh, there it is. It's figure 1-11. Oh, I'm not able to see it, but are you able to see this little figure there? Is it at all visible?
It's a little blurry.
Yeah, so just go on your books and see figure 1-11. It shows the general state of stress on which all these 6 faces have normal stresses, all the 6 faces have shear stresses. That's called the general. Maybe I have it on my site also. Let me show you those. This is the formation of the shearing stresses on each face. No, I don't. Well, let's move on then to the next topic, which is stresses depend upon cross-sectional area. So look at the picture I'm showing you now on the slide. It is that of a member shown in 3 dimensions, and then there is a tensile force of P applied on either side. So what we defined our normal stress was the load P, which is this, divided by the perpendicular cross-sectional area, which is this. So P over A will be the normal stress there. And if you were to apply the same load on this surface, P, then you can also find tau taking this area and dividing P by that area. So, but the fact that the thing that we want to point out here is that the normal stress will obviously depend upon the area. So if area is so much, P divided by this area will give you one value of sigma. But if for some reason you are interested in finding the stress on an area which is inclined, which is not 90 degrees, which is inclined, then this would be, as you can see, the area has increased, so the stress will be reduced on this inclined plane. And to find that, there's an example, the next example coming is of this kind. You will be able to see what I mean there. So any questions, anybody, before I go and start solving problems? Let's do the first problem then, which is this. Please read the problem. There we go. Determine the average normal and average shear stress acting on the cut section AA. So whereas the force applied is 1000 Newton, which is perpendicular to the cross-sectional area. This is an axial force we've applied. But the man wants you to find the normal, the stress. He's just saying determine the average normal and shear stress acting on the cut section AA. That's where we want to find. And the dimensions of the cross-sectional area there are given as 0.05 meters by 0.05 meters. So my first question to you is, if you were to find the normal stress on this area, what will that be? It will be 1000 divided by the cross-sectional area, which is 0.05 multiplied by 0.05. 0.05 times 0.05. So if you divide 1000 by that area, you will get the normal stress on this area. But he's asking us to find the normal stress on this inclined area. Let's do that. So I'm trying to draw kind of a 3D view so that you can appreciate what is the difference between the two areas. You see what we have done? This is the cross section AA. And this is, the angle here is 30 degrees, this one. Now, which side is 0.05? Well, this is 0.05 and so is this 0.05. I'm sorry, the drawing doesn't seem to be showing that, but they are both equal. 0.05 by 0.05, that is what is given. But the man wants us to find the stress on this area. So what will be this area? This area will be 0.05 multiplied by this length. And how do we find that length? Well, I can say sine of 30 will be the opposite over hypotenuse. So 0.05 divided by L, or L will be equal to 0.05 over sine 30, which is 1 over 2, which is 0.10 meters. So this L comes out to 0.1 meters. Everybody good? And the area which we are interested in, therefore, area is equal to, therefore, the area will be 0.05 times 0.10, which is 0.005 meters squared. That's just kind of the area that we are interested in. So now let's look at the two-dimensional view. It looks something like this. And there is my force of 1000 newtons. Now, if I want to find the normal stress on this area, I need to know what is the normal force on this. You see what I'm saying? And also I should know, so if I divide this, given 1000 force, if this is 30, then this is also going to be 30. Alternate angles. So what will be 1000 cosine of 30 will be this force, and 1000 sine of 30 will be this one. So the normal force will be 1000 sine 30 which is 500 newtons. And this will be 1000. The parallel force would be, let's call that V. The shear force would be 1000 cosine 30, which would be 1000 times 0.866, which would be 866 newtons. Everybody good? We just resolved that given 1000 Newton force into its two components, one normal to the area, one parallel to the area. The one normal to the area will cause the normal stress, which is sigma. Sigma is defined as P over A or N over A, you can call it. And this would be, N came out to 500. And what is that area? That area we already found was 0.005 meter square. So Newton per meter square is Pascal, and this comes out to 100,000 Newton per meter square. Or you can also call it 100 kilopascal. So kilo is 1000 pascals, right? That's the answer number one. What are the stresses? What is the normal stress on the inclined plane? Well, it is this 100 kilo. And to find the shearing stress, we will need the shear force, which is parallel to the area, which is 866 newtons. So tau will be equal to V over A will be equal to 866 divided by the same area, which is 0.005 meters square. Again, Newton per meter square is pascals, and this comes out to 173,340 pascals, or 173 kilopascals.
Excuse me, Dr. Rother.
Yeah.
How did you get the 866?
So this was 1000 cosine of 30.
Oh, okay.
That was sine 30, this is cosine 30. And cosine 30 is 0.866, so multiplied by 1000, it becomes 866 newtons.
Okay, thank you.
So this is the, now coming, just talking about the same thing as I was, what I'm saying is that on this surface, the tau is what we just found, 173 kilopascals. So if I were to take an element from here, so, and draw it there, let's say like this. Well, actually, it'll be easier for you to visualize if I draw it at the same angle. So let's say, maybe I can draw it there. This is 173 shown there on the top surface. What will be the shear stresses on these three faces now? Can you figure out? Yeah, this one will be 173 in this direction. This one will be 173 in that direction, and lastly this. So they will all be 173, and they will have those directions also. This is the element I have taken from this, from here somewhere like this. Everybody good? So those are the answers. We got sigma equal to 100 kilopascals, This was the normal stress. And the tau is shown as minus 173 kilopascal. Why minus there? Let me show you. So for the normal stress, as you know, the tensile stresses are taken, the sign convention is tensile stresses are positive and compressive are negative. So that is why this is a positive normal stress. And for shear stresses, the sign convention is, let me show it to you here. If this is a shear stress in this direction, then this will be the shear stresses that will follow. Tau. So, well, I was trying to show you the sign convention. Sorry, not this. This I've already drawn. The sign convention for shear stresses is as follows. So, if you have an element, then the right face downward is considered a positive shear stress. This is considered a positive shear stress, and this will result in these other stresses. So left face upward is positive, right face downward is positive. So in this case, because our right face came out going up, as opposed to this is positive. This will be negative then. So this is 173. That is why the negative sign is put there. You see what I'm saying? It's not a very critical thing. I don't think this is used much, the positive, negative, as I said. But just for your information, you should know that the right face going down is considered positive. Right face going up will therefore be negative. Any questions, anybody? Everybody good? So let me go ahead and do the next question, which is this. Or before that, we need to talk something about single and double shear in pins. Now, this is something I need to explain to you, and somebody already asked a question on this also. So let's look at this member. This member is supported at two ends. On one end, I have a pin like this. And on the other end, it is supported by a cord, which is also kind of a pin on this end. So, but if you see the details of these pins, they seem to be different. Look at this pin B first, for example. Pin B is something like this. And if you apply a load here, this end will have a tendency to go down, but the cable will be holding it. So cable is pulling it that way and the load is pulling it downwards. So if you imagine the pin, the area of the pin right there, this will be under shear because it is being pulled in the opposite directions. And the force applied on the pin is parallel to the cross-sectional area of the pin. You see what I'm saying? And it will be kind of resisted by just one face, one cross-sectional area of the pin. So that is why this pin is called to be in single shear. But as opposed to that, if you see the construction of this pin, it is a little different. This pin is holding this member in this way. And once again, this load will be trying to pull it down in a way, trying to pull it in this picture. If you have to see, it will be kind of pulling it this way. And you can see now it will be resisted by two of these surfaces. You see what I'm saying? So the area will be doubled there. Here it was resisted by only one surface. There it is being resisted by two surfaces. So this is a pin in double shear. This is a pin in single shear. When you use pin in double shear, you have to double the area. So shear force will be V divided by twice the area because there are two areas. And this will be only one area, V divided by the area. This is how we define single and double shear. And some detailed pictures are also shown in this case. If this was the force applied, there will be the shear force will be divided into two surfaces, this way and that way. Either you can half the load applied V and then VA divided by one area, or you can take the whole force and divide it by two areas, the same thing. This is a single shear case in which the entire force is taken by only one surface. So let's do this problem now. Any questions on this, anybody? Single and double shear.
Nope.
Good. So whenever either you will be told that the pin is in double shear or single shear, or the drawing will be enough for you to decide whether this is double shear or single shear. You should be able to, from the detailed drawing, decide whether this is single shear or double shear. Please understand this. It will be your responsibility. Many times it may be given in the problem that the pin is in single shear, or the pin is in double shear, but if it is not written, then you have to decide based on the construction which is shown there. So let's try and solve this problem. Read this problem, please. Determine the average shear stress developed in pin A. This is pin A of the truss. So this is the truss, and there is a pin in all the three. There is a pin at A, pin at B, and pin at C. And the man is saying that the horizontal force P is 40 kilonewton applied at joint C. So this is 40 kilonewtons. Each pin has a diameter of 25 millimeter and is subjected to double shear. So all the pins are in double shear. And he wants you to find the shear stress in pin A only. And the construction is also shown. It's written double shear, and it is shown also it is in double shear. So we are going to find the shearing stress in pin A, which is in double shear. Everybody good? Let's do that. So if you want to find, let me just get this thing cleaned up. First thing we need to do is find support reaction. So let's say this is our truss. I got a pin at A, so the pin is replaced by AY and AX, let's say. And then there is a roller at end B, so that is replaced by BY. And there is a 40 kilonewton force applied there. And this is my x-axis. This is my y-axis. So the first thing we need to do is to find AX and AY, because those are the forces that will really cause the shear in that pin. So to find that, we have drawn this free body diagram, and now I can take some forces in x direction equal to 0. Can I say AX is equal to 0 by inspection? No, because there is another force in x direction. So I will say minus AX plus 40 kilonewton equal to 0, or AX equal to 40 in this direction, 40 kilonewtons. What about AY? How do we find AY? Well, we can take moments at B. This is the end. B, this is A. If I take moments at B, what I can see is AX will not contribute because it is passing through B, its line of action is passing through B, but these two will. So 40 kilonewtons will have a clockwise moment at B. What will be the value of that? It is clockwise, so it will be minus. I will say minus 40 times. What is the moment arm there? 1.5 exactly, thank you. And then AY will have another moment also. It will be a clockwise moment, so that will also be negative AY times. What's the moment arm there? 2 meters equal to 0. Therefore, AY will be 40 times 1.5, and it will be really minus divided by 2, which is 30 kilonewtons. In other words, we found AX is 40 kilonewtons and AY is 30 kilonewtons. But it came out negative, which means it is in the opposite direction. So I got to make sure I'll write it as AY is equal to minus 30 kilonewtons rather than 30 because I've shown it acting up. So it will be AY will be minus 30 kilonewtons. So if I were to draw the force diagram for pin A, it will look something like this. There is a 40 kilonewton that side, and there is a 30 kilonewton this way. So what is the total force on this? The total force will be the sum of these two, which by law of parallelogram forces will be this. Let's call this force A. And A will be equal to what? This is 30, this is 40. Therefore, A is equal to the square root of 30 squared plus 40 squared. And this will come out to 50 kilonewtons. So the total force acting on the pin is 50 kilonewtons. Now, if you look at that pin, it has a force which is 50 kilonewtons, and because the pin is in double shear, therefore tau will be equal to V over A. In this case, in case of double shear, you know that either you half the V, so it will become V over 2 divided by the area. And V we found was 50, so 50 divided by 2 would be 25 kilonewton divided by area would be, the diameter is given as 25 millimeters. So you convert that into meters and then find the area by doing pi d square over 4. Let me just do it here. Area will be pi into d square, and d is 0.025 whole square divided by 4. I haven't calculated it separately, but now I can put this value there and I'll find tau is there. Can you see the last line that I'm writing, or is it not visible on your screen? So let me go up. I suspected that much. Let me come back here. So therefore, tau is equal to 50 divided by 2 because of the double shear. The force we found was 50, but we had to divide it by 2. And then area we have found is pi 0.025 square divided by 4. And when you calculate all this, the number came out to 50,000. So this is kilonewtons also, remember. So it came out to 50,930 kilopascal. And we can also write it as, in terms of megapascal, it will be 50.9 megapascals. That's the final answer. That's the shearing stress faced by that pin, 50 megapascals. Any questions, anybody?
I have a question.
Yeah.
What is it divided by 4 on the area?
That's the area of a circle, pi d squared over 4.
Okay, thank you.
Because if you use radius, then it is pi r squared, but if here the diameter was given, so we use pi d squared over 4. Any other questions? Well, it seems that my time is up for the class. There's one more question, and I think I have put the solution for that also for you. This is the final answer we just got. And here's the solution I have put for this problem. And then the next problem is this. I'd like you to try and do it at home in your own time. It is similar. It has this load, and then he's asking you to determine the average normal stress developed in rod AB. So rod AB is this. So if you want to find the normal stress, what do you have to do? You have to find the axial load on this. And that you can find by drawing the free body diagram of pin A. But I think I have put the solution also. Here's the answer. I'd like you to do this. If you cannot, if you get stuck somewhere, then here is the solution also given. And then this is the yellow page. I'd like you to do some reading tonight. This is your homework for tonight. Section 1.3 to 1.5. This is what we've covered today. You ought to read these. Then there are yellow pages 5, 6, 7, 8. 4 yellow pages. And then 3 homework problems. You've got to do all of them today. By the way, I did check mastering before starting the class today. 26 people have now registered, all right, but only I think 8 or 9 people started doing the homework. Yesterday, you were supposed to do 2 problems, only 6, 7 people have done it. Or 8, 9 people have done it, not more. I am again reminding you, please do every day's homework every day. That will help you in understanding and keeping pace with the class. Any questions, anybody? Otherwise, I'm done.
All
I
right,
will
thank you,
stop
Professor.